Good. All right, good morning, everybody. Thanks for coming and joining us today. It looks like our weather today will be a little bit nicer. So today we're going to kick off the second day of the Cultural Astronomy School. I hope everybody has enjoyed the talks yesterday and the planetarium and dinner and trivia last night. Thanks to Gerhard for organizing the trivia. So today we're going to have a series of lectures looking at more quantitative sides of cultural astronomy. But before we have our first talk, I do want to say, make a bit of a statement that despite things that may have been said yesterday, which I found entirely unacceptable, that we are 100% committed in our group to supporting women and girls in STEM and Indigenous people in STEM, and that there is no such thing as political correctness gone mad. We are completely supportive of bringing diverse views into research and teaching and engagement and everything we're doing within this group. That is something we are 100% committed to without question. So what we have today is a guest lecture. Unfortunately, César González-García was going to join us, but got COVID just a few days ago. Yeah, so he very kindly got online and recorded a video of his lecture. And you'll have to, I'm not sure the situation, but he is very sick at the moment, but was still very willing to and very generous in giving his time to create this so we could see it. So the first session is going to be the video, and then we're going to have coffee break. We'll have lunch again. The lunch is going to be extended a little bit today. So we're going to have about an hour and a half for lunch. Again, same thing as yesterday. We're going to go to University House. They've got our box lunches. We'll sit in the same location. If the weather continues to improve as it is now, then we will, you have the option of sitting outside. But we'll have that sorted today. We'll have an afternoon tea and then a couple more speakers later today, which will include Gail and Georg. Yes, exactly right. And Morgan. Where'd Morgan go? Morgan's gone. So we have a few people who are going to be talking about, methodologies and approaches and more the technical aspects of archaeoastronomy. So without further ado,
good morning. In this lecture that I'm recording right now, I am trying to explore how to gather the data that we need to do archaeoastronomy research, and try to show a few ways to analyze this data to extract the information that we can find from this data, and trying to see how the data can tell us something on the possible astronomical meaning of these orientations. I first need to apologize for not being there in person. I was tested positive in COVID last week, and I couldn't make it to the flight before testing negative. I will be there for the conference though, and I will try to see most of you next week then. But in the meantime, I decided to record this lecture so that at least you can have this workshop on how to collect the data and analyzing this for archaeoastronomy. So let's go ahead. First, it is what data do we need for archaeoastronomy? And well, as you can see here, I like this movie, The Good, the Bad and the Ugly, and especially for the data gathering, I think it is a very nice metaphor of the process of data gathering, data analysis, and data presentation. Going from the ugly to the bad and probably the good. That is finally the results that we want to show and extract from our data. So for this archaeoastronomical data, we need three magnitudes, and these are the azimuth, the altitude of the horizon, and the latitude of the site where we are taking the data from. I won't go into the details of the astronomical differences between azimuth, why the altitude of the horizon is important, and also recording the latitude of the site. I will give this as a known knowledge, but these are the three magnitudes that we need to record when we are on site, and we will see how to do it, where to do it, and the accuracy that we would need to reach to suitable results. Of course, to do this, we need to understand our data, and we will also see how we can understand this data. To do this, we need to do many measurements and to understand where are the pitfalls and the limits of this data gathering. Also, we need to know what must not be done. I mean, up to where we can push the limits of our data, and what can be extracted and what cannot be extracted from our data. And to do that, we need to quantify the quality of our data. And well, we will try to assess all these along the workshop. To begin with, I would like to present a couple of cases where a trained eye might sometimes lead us to spurious results. For example, in this case, we have a house in the northern part of Europe, where on the 4th of April, as it says on the area here, we can see that the setting sun enters through a window at a very narrow angle in an apartment at the top of a building. The light of the sun passes through the two keyholes of the main entrance, here you can see, and get projected on the opposite wall in the staircase as a double sunset. And we could say, okay, this is interesting, this is funny, but is it relevant? And to know if it is relevant or not, we always need to take into account the context. And in this case, it's pretty obvious that the context is telling us, okay, this is just a flat of apartments where out of pure chance this happens on a given day, for example the 4th of April, and nothing more can be extracted from this. This is just pure chance. Okay, fine, fair enough, but now let's move to the second case. This is what you can see from the window of my home. I'm living in Santiago de Compostela in the north of Spain. It is a pilgrimage center. It's the end of the Camino de Santiago, and this is what you can see in the front, in the central part of this picture, is the Cathedral of St. James, where supposedly Apostle James is buried. and is the focus of this pilgrimage route that moves millions of people along the years to gather here, especially at particular dates in the year, coinciding with some of the festivities celebrated to St. James. Well, you can see here that the sun rising on the winter solstice. Okay, fair enough. Is winter solstice important for the celebration of St. James? In principle, not, because St. James is celebrated on the 25th of July. So on the other opposite side of the year, we are here nearly at the end of December. But St. James has many different festivities. In particular, it has 3 of them due to a complex legend that I won't go into details here. But let me tell you that one of the festivities is on the 30th of December, just 1 week after the winter solstice. And you can see the winter solstice here happening, rising from my home place, right behind the cathedral, on the days very close to the celebration of this festivity of St. James. Curious enough. We are connecting now a date that is relevant with the location where we are doing the observations from. So you can see here that the sun is rising from behind the cathedral on the dates close to the 30th of December. Interestingly enough, this is the view from my window, and you can see that also there is also another church here, very large. It is St. Martin, and well, the rising of the sun right behind St. Martin happens also on the 11th of November, the day of St. Martin. And also you can see that on the edge there is another church, St. Francis, and the rising of the sun right behind St. Francis happens on the 4th of October. The church celebrates St. Francis on the 4th of October. Oh, so we have 3 sites, relevant sites of the landscape in Santiago, and in this case the 3 of them could be related to the sighting of the sun rising behind them from my place on the relevant places, on relevant dates for the celebration of these saints. So is there anything relevant on the spot where I'm doing these observations? Well, yes, it is the house of an archaeoastronomer. What's the better place to have a house where you can see these impressive alignments, if you want to call them this way? So context tell us that, okay, this could be relevant or not. Well, as we will see later, no. As you can imagine, this is just, it is true that the sun rises here on the 30th of December, 11th of November, 4th of October. I can show you the pictures, but it is also true that my eye is guiding this, and also it is true that the churches span for a wide range of horizon, so there are a lot of possible dates that they are not the 30th of December, the 11th of November, the 4th of October, that they would also coincide with these orientations, and they do not have anything to do with the church celebrating feasts for these churches. So we should be very careful, very careful when dealing with data and trying to extract information and conclusions and interpretations from them. In order to do this, in many occasions, we will try to compare the data from one site with many others. As Arthur Conan Doyle said in The Sign of Four, while the individual man is an unsolvable puzzle, in the aggregate he becomes a mathematical certainty. You can, for example, never foretell what anyone would do, but you can say with precision what an average number will be up to. Individuals vary, but percentages remain constant. So say the statistician. But at the same time, we must always be careful, because torture numbers and they will confess to anything. So with this in mind, that we need to be careful, that we need to treat data in a fair way, and with that we always need to take into account the context, it is how we are going to proceed in the following minutes with how to gather data and acquire our data from in the field. So let us see how we gather our data. The first thing to do is try to understand the site where we are going to take the data from. For instance, in this case that we have a map, the plan of pre-Roman temple from the island of Sardinia, we can see that it has a clear axis of symmetry. It has an entrance here, denoted by these circles, indicating that there is some columns here, and there is the entrance to the sacred area. So we may say, okay, the important direction here is from the inside out in this line, and we see that in the front of the temple we have this landscape. This is a mountain, and it is important to notice that we are going to be interested in the altitude of the horizon. We will see this in a moment. So the two magnitudes that we are going to measure here, or the three, better to say, is the azimuth, which is the angle with respect to true north. This is north, and this is the direction that we are interested in, and we need to know the azimuth. Then the second magnitude is the altitude of the horizon. This is an angular scale, not the altitude in meters above sea level. This is nothing that we are interested in right now, but the angle that subtends this altitude, this mountain in this case. Okay, and the third number would be the latitude. The latitude were that of the site, in this case of this temple, and with these three numbers, azimuth, altitude, and the latitude, this is the basic data that we are going to need in this case. In a second version of this map that we saw before, here we have the same temple or a similar one, and this is the direction that indicates from the inside out the azimuth. You see this direction, and this angle, the azimuth with respect to north, is the one that we are going to measure in this case. Now the altitude, this is an angle again. This is the altitude, this angle between these two lines is the one that we are going to be interested in. Why? Because since the real azimuth, the real horizon is going to be rugged by mountains, valleys, notches, and everything, this is the real area where I'm going to see stars rising or setting, or the sun or the moon rising or setting as well. And this is the ones that I'm going to be interested in for archaeoastronomy. So to say, I'm not going to be interested in the theoretical line of the flat horizon here, because I'm not going to see the sun or the stars rising right here, but above the real horizon. And to do this and to take into account this real horizon, especially at middle and high latitudes, I need to take into account the altitude of the horizon. And as I said, azimuth, altitude of the horizon, and the third magnitude is the latitude. The latitude that I can measure, for example, with a GPS or nowadays with a smartphone. So then now, how I'm going to obtain this azimuth and this altitude of the horizon, provided that I have the latitude from this GPS, or imagine that I have it from literature that somebody else has obtained this position, the latitude of this site. How do I measure the azimuth and the altitude? Well, the first and easiest way to measure this probably is going to be from a map. No need to go into the field in this case, if somebody else has done a well done map and a very detailed one. And imagine that in this case, this is the map of a megalithic structure in the northern parts of Germany, and I want to measure the orientation of this megalithic structure, the Fischbecker-Bräutigam. You can see here that I have the north that is given in the left side of this map, and then I can draw a parallel line to this north and the orientation that I'm interested in. Then the azimuth is going to be this angle, provided this north is true north. And this is a very important and key issue when dealing with measurements on a map, because in many occasions, especially in old maps, we don't have the information of this north, if it is true north or if it is a magnetic north. In some cases, we are lucky enough that the author indicates this is magnetic north, and if we know the time, or at least the year when this map was drawn, we can calculate the difference at that time of magnetic and true north, because there are models and there were measurements at the time, and we can correct from this. We will see that in a moment. If not, this is going to be just an approximation, because if we are not sure that this is a true north, we are not going to be 100% confident that the orientation is well taken. And this is something that you always need to keep in mind. As a good friend of mine used to say, no data is better than bad data. So many times, if you use bad data, you are going to run into wrong conclusions. So in this case, be sure that if you are using this kind of maps, the north, you know that it is either true north or magnetic north that you can correct. Okay? In this case, for example, what we would do, it would be to use in this, this is what I used in this case, an online protractor. You can use physical, real, flexible one of these that we have always used at school, and measure this angle between north and the orientation that I want. And in this case, it would be something above 90 degrees. I cannot see right now the numbers, but you can see this. It would give you the orientation of this megalithic structure in this case. The problem with maps is that we are not obtaining the second magnitude that that we need to obtain the full archaeoastronomical data, which is the altitude of the horizon. We will see in a moment how can we deal with this when we don't have the possibility to measure this altitude of the horizon. But let us first see the methods to obtain the azimuth. Okay, this is the first and easiest one. The second would be that the second just in the line of methods that I use here, not just because this is the first and is the most or the best. No, it's just the first in this list. The second would be going into the field and measuring the orientation either with a theodolite or, for instance, with a compass. If you use a theodolite, you need to rely on some reference lines, because in many occasions you don't know exactly where north is going to be. You draw a line with two roads, for example. That is going to be your reference line once you have your theodolite set in position, and then you measure the angle of the, in this case, for example, the corridor of this dolmen. You measure this line with respect to this reference line. Okay, so you say, for instance, that it is whatever 30 degrees west of this line. You have this azimuth. Then we need to correct the reference line with respect to north, to true north. And to do this, we need to find different solutions. For example, the easiest one would be to find different points in the landscape that I can recognize from the spot where I have placed the theodolite, in this case, or total station. It would work much better because in this case you have the reference line inside the machine. But if in case you only have the theodolite, then this north is going to be estimated from the triangulation of different lines of different points in the horizon. Okay, and with this triangulation you take the reference line with respect to north, and then you can correct this azimuth that you have estimated before with north, with true north, and in this way you obtain azimuth. Probably this is a very accurate way of obtaining azimuth lines, even more if you use a total station. However, in many occasions we don't need such a high accuracy given the state of our remains. For example, in this case, this megalithic structure that it has the sides of the corridor are sloping and is rugged, and there is going to be an intrinsic uncertainty much larger than the uncertainty that you are going to have by using a theodolite or a total station, or even the one that you are going to have if you use a professional compass like this one here. This one includes two items. You have a compass and a clinometer. With the compass, directly you face with the compass in the direction that you are interested in, for example the direction of the azimuth, or in this case the direction of this lighthouse here. You look through the eyepiece at the bottom, and you can see here different numbers. When you use this kind of devices, normally it has two scales. One is going to give you the direct measurement, meaning in this direction, in the direction you are looking to, and with a small size numbers you are going to have the reverse direction, so in the other direction, just in case that you are not able to take the measurement in the direction you are supposed to do it. They will provide you with this, and you don't need to subtract the 180 degrees. You can have it here in the reading. But in this case, for example, you may have the correct direction. In this case is true north, just facing the lighthouse, and then finally what you need to do is, once you have your reading, remember that if you have used a compass, or for example if you want to correct from the map that you know that it has a magnetic north reading, then you need to correct from magnetic declination. Remember that the Earth is a magnetic body, but the north magnetic pole or the south magnetic poles, they don't correspond to the positions of the geographic poles. There is a difference, and this difference, as seen from different points from Earth, is what is called the magnetic declination, the difference in angle between the direction of true north and magnetic north. Okay, in this case we're going to use this tool from the American administration, where we have models that they provide the magnetic declination for a given position on the globe and for a given date. This is why we need to know, for example, in the readings taken from maps, when this map was drawn, because if it includes the magnetic north and we want to correct, we need to know this date. Also, if we take the readings at a given moment, we always need to take a note of the date, okay, to remember later when we are at the office to include here. So this is useful, as I say, for map measurements, but also for magnetic readings, for instance, the compass that we have just seen. And it is important, as I say, to incorporate the date, to know exactly the date, to include it here, as we will see. To make life easier, there is a mobile version, an app of this website, where you can either just introduce the latitude and longitude, or it takes them from the GPS in your mobile and calculates the magnetic declination for you. So the first thing that we need to include here are longitude and longitude. So we need to record these if we are on the field, or if we have it from a map, then we need to know them. We also need the date, as I said, and it will provide this value. Once we set it to calculate, it will open this new window where it will give us here the value of the magnetic declination. And this is very important because, for example, in this case it is more than 1 degree west. This means that there is a change between the magnetic north, that is a little bit towards west, and true north. So my readings need to be corrected from this value. In this case, if it is west, I need to subtract from my readings this value. When it is east, I need to add these readings, this correction to my readings, to my values. Another very useful tool today for obtaining orientations, and one that has been extensively used in the past years, is Google Earth. Google Earth, as you know, is a tool that uses satellite images, like this one, for example, of the Hatshepsut temple in Deir el-Bahari, to obtain viewings where you can also change a little bit the point of view, the exact point of view, and you can fly by. You can also include 3D images. You can change the illumination of the images. You can do many things with Google Earth, but and it has the capability of providing azimuths as well in among the different tools that you can see here, but it has some problems as well, as we will see some of them. Here you have a number of tools that you can use, different draw different kind of lines and perform different kinds of calculations of sizes and for example paths and distances and everything. The key tool for measuring orientations in our case is going to be this one, the ruler here on top. Once you press, you have here that it appears a number of options. You will see that your pointer is going to change, and then you need to click from one point in the screen to another point in the screen, and it will give you the direction. Well, it will give you different quantities between these 2 points. One of them, as you can see here in the small gray window, it is the longitude on the map. So this is in meters, for example. It is 241 meters. Distance on ground, imagine that you have different shapes of ground, then it will try to accommodate this as well, and they will give you a different measurement. In this case it's not that different because there is no so much rugged terrain in here. And the last number is the direction. This direction, it is a calculation that it does to provide you the azimuth. So this is the azimuth in degrees with respect to true north in principle. So in this case, for example, you can see that for the temple of Hatshepsut in Deir el-Bahari, I have a direction of 117 degrees with respect to true north. I can, for example, try to do many other things with this tool, but this is the basic. And with this, I have the orientation. This is very handy, but Google Earth is going to give me these values provided I use this image. But if you can see, this image has something weird in it, because I can see the sides of the temple. For example, look at the ramparts here in the center of the image. You can see that I can see the southern part of the rampart. So the image is not completely perpendicular, because of course, I mean, these satellite images are wide images, and it would be very lucky that the satellite is right on top of Deir el-Bahari to take this image from a very perpendicular line. So probably it's going to be a few kilometers or several hundreds of kilometers away, so that when looking at this, is looking from a given angle with a given parallax, and so I can see the size, the side of the temple, and this introduces an uncertainty in my measurements. So this is why I say that these kind of tools, they are very useful, but you need to know the problems that you may have. To certain this problem somehow, one could use another tool that Google Earth is giving us, and this one is provided by this other tool on the left of the ruler tool, which is this clock that you have here with an arrow, a round arrow around it. And it is because if you go to the bottom of this image, you can see that this image was taken somewhere in 2021. If you go to, for instance, the previous image, just using this tool, you can select another image. You can see that the line that you have drawn from your previous image, now it doesn't define the orientation anymore. It's going to be slightly different. So the uncertainty, a way to acknowledge the uncertainty in our measurements with Google Earth, is taking as many measurements in several of these images, the image of 2021, the image of 2019, 2018, 2015. If I can take different measurements at different times with different images, and then average them out to obtain a mean with an uncertainty that is going to be given by the variations between the different images. Okay, so my measurement is not going to be the one from just one image, but it's going to be the mean of these different images with an uncertainty of these different variations of the readings that I have from different years. Okay. Well, before moving to other tools that we may use to obtain measurements, Google Earth has another capability, that is that we can obtain the altitude of the horizon as seen from the side of our interest. In this case, we can go back to the ruler tool and draw a line with the same direction that we had the measurement done before, but we make it, as you can see here in red, much larger, much longer than the one that we were obtaining before. In this way, we can save it. As you can see here in the bottom part of our gray window here, we save it, we give it a name and whatever, and at the end we obtain this red line. When we right click with the mouse on top of it, it will offer different options, like deleting this line, changing the name, etc. And one of these options is the profile, the profile of the terrain along this line, this red line. And this is what I can see in the bottom part of this image. This is going to give me from left to right, in this case, how the altitude in meters above sea level changes with the direction. And in this case, for example, I can estimate that from the left position, where in this case the Hatshepsut temple is located, the last part of the horizon, the last part of the landscape I'm going to see is this, the one that is at the highest point in this case, and so the difference in altitude divided by the difference, the distance between these 2 points, is going to give me the tangent of the altitude of the horizon. So with this I can calculate the angular altitude of the horizon. Is nothing more than the arc tangent of this difference between the altitudes in meters above sea level and the distance between these 2 points. Okay, so we use this. Another capability that has Google Earth is that we can try to mimic in a rough way how we would see the sky from a given position. For example, here we have an image of the Cueva de Menga. Menga is a huge megalithic tomb in the southern part of Spain, and we could see how the landscape is from on top of this mound. To do this, we just take the figure of the human here on the right, we take it with our mouse and drop it on top of the position that where we want to calculate the panorama from. With this, we obtain a somehow realistic depiction of the landscape, and you can see that in the direction of the monument there is this mountain. Actually this mountain is called Peña de los Enamorados. It has a very specific and characteristic profile when you're on the ground, but in this case it appears much softer because our model of the terrain is quite rugged here. It doesn't have enough details, but in any case we can use the tool that you can see on top of the Google Earth image next to the watch that we used before. You could see like a sun rising on top of a horizon. There you can use the gears to calculate different moments that you're interested in. For example, I would be interested not only in seeing how the sky is looking at that moment, but also, for example, to see how the sunrise at summer solstice is happening away from where this mountain is located. And in this way I can verify if my direction of interest has anything to do, in this case, with summer solstice or not. We can do very similar calculations to Google Earth, which are based on different satellites with other kinds of orthophotographic tools. For example, those obtained by drones, like the ones here, where I can obtain again directions, and given that these images they may have also information on the altitude of the terrain. I can make some digital terrain models, and then I can do some calculations also on the altitude of the horizon and other characteristics. This can also be done with geoportals and other tools that each country has for the orthophotography facilities normally within the geographic institute of each country. For example, here you can see the tool of the Spanish geographic geoportal, where all of this is for free. You can use it, and also you can download models of the terrain obtained with a LiDAR, with a type of laser scanning of the terrain with a resolution of below the meter, so you can have a very detailed modeling of the terrain that you're interested in. And here you have some tools where you can also do measurements of directions and altitudes of the horizon, with the characteristic that in these cases most of the images are very well corrected to have the orthogonal direction well taken into account. Of course, you can use GIS software. GIS stands for Geographical Information Systems, like for instance the ArcGIS or QGIS. One is open source, the other one is a commercial tool, where you may have also some very useful capabilities for defining directions and obtaining azimuths and so on. This is not, I'm not going to provide any introduction to this, because it has a large and very steep learning curve, but they are very potent, flexible, and they allow for massive calculations, and there are libraries with calculations to perform archaeoastronomical research in them. So just please go to some of these manuals, or just drop me a line if you need some help with this. They are very useful, but they would need some very specific and dedicated time to this. That in this wide review of different ways of obtaining measurements with different tools is going to be out of the scope of this lecture. So with this, I would finish the part of the obtaining the azimuth with these kind of tools. We have seen measurements with a map, measurements with on the ground, either with a magnetic device as a compass, or with a theodolite, or with a total station. We can use satellite imagery with Google Earth. We can use orthophotography with drones or the geoportals, and also the GIS software. So how to obtain the horizon altitude? We have seen one way, that is with Google Earth. We have seen already that our horizon altitude is going to be this angle that subtends this portion of the landscape in the direction that I'm interested in. Okay, for instance, in this case, what we are looking at is the forum of a Roman town in the south of Spain, where you can see that we can measure the azimuth, but the altitude of the horizon in this case is difficult to estimate. We could use it, for example, with the theodolite. It is just taking the angle between the lines in that direction. So when I put the small telescope on top, I will have the reading of what is the angle that I have to put the visor up or down, and this is the altitude of the horizon. The same thing with total station, also with clinometer. Remember the tandem that I had before with the compass and the clinometer. With the clinometer, I can also estimate the altitude of the horizon. And in this case, I'm going to use something different, because if I'm on the terrain in this town, it is surrounded by buildings, the forum. So I cannot see the actual horizon. I will see a horizon blocked by buildings, or sometimes if we are in the middle of a forest, we are going to measure and we see only trees, and we don't see the actual horizon. So there are tools using, for instance, digital terrain models, as we have seen before. We have seen Google Earth, but there are other tools, like for example Hayward's Stat, or Peak Finder, which is actually I'm not going to show it, but it provides nowadays a much better resolution than Hayward's Stat, but I will show Hayward's Stat anyway. We can go to the map where you have of the site where we have obtained this measurement before of the azimuth. In this case with Hayward's Stat, it is located very close to Gibraltar, here next to the city of Algeciras. And here you see the direction we are interested in is in this direction, close to the direction of the rock, and we can go in Hayward's Stat in this direction and see in the map the altitude of this horizon in this direction. We have it on the bottom of this line, the bearing of 126 degrees and an altitude of 0.7 degrees. This is in the bottom part of this image. So my altitude in this case is this 0.7 degrees, and my bearing, my azimuth, is 126.5 degrees in this case. So with this and the latitude, remember, latitude, azimuth, altitude of the horizon, latitude, azimuth, altitude of the horizon, these three numbers are the ones that I need for the obtaining the data needed for archaeoastronomy. In the next lecture, Gail is going to talk about horizon. This is a very interesting tool. I won't go into details, but you can also use it. She will also much better than I explain all these, where you have you can introduce digital terrain models and with a number of settings produce very interesting panoramas where you can see how the profile for a given direction is, also obtaining distances to different parts of the horizon and realistic measurements, for instance, for the rising and setting of different bodies. I will skip this part because Gail is going to treat it much better than I will do. And let me finish just with a couple of slides these parts of data gathering. The first is going to be about mobile applications. Nowadays, most of us we have smartphones or tablets or iPads that they have cameras and they have gyroscopes, and they also include a compass. So there are apps where we can measure the directions. For instance, in this picture, the direction, the azimuth is going to be 289 degrees with a difference of 18 degrees west of north, and I can also estimate the altitude of the horizon and so on. However, these are very sensitive and very difficult and very poorly accurate devices. They need to be extremely well calibrated. They need to be very well handled. Otherwise, slight variations are going to affect the readings. There are tools that actually that we have developed that may be used to obtain the azimuth, the altitude, and the altitude, the inclination, and the latitude of the site. So all the measurements that we need to do a reading. For instance, here I'm doing this with a dolmen in the north of Spain, but these systems are very sensitive to the presence of any metal, of any kind of magnetic and electromagnetic variation. And for instance, in this case, the difference between the reading with the application and the actual reading done with a compass corrected with magnetic declination or with a theodolite is a difference of above 3 degrees. So they could be useful, but remember that they are not very accurate. Also, we have used it, for instance, here in Rome with similar problems, with a slight difference, even larger in this case, of 5 degrees in difference. So there are problems, and we need to take them into account. And these problems and these uncertainties are going to be important, very important, in the data reduction and data handling that we are going to treat right in the next section. So once we have our data, remember we have our azimuth, we have our altitude of the horizon, we have our latitude of the site, we can try to see if there is any astronomical connection in the direction that we are interested in. And this is done through this formula here. Remember, we have azimuth, the capital A, we have the altitude of the horizon, h, and we have our latitude, phi, here. And with this formula, we are going to obtain delta, which is the declination. The declination of is the astronomical declination, and this is a magnitude that is giving us the path of any astronomical body night by night. So once we have the declination, we can try to find if there is any astronomical body connected to that direction. There is software devoted to do this, and we are going to summarize some of them in the next slides. The first software we are going to treat is the DECPAC site by Clive Ruggles. There is another one, this one, Declination on Render, that it was made by me, where you can also include your data, your azimuth, your altitude of the horizon, your latitude, and obtain the declination. The difference between the two of them is basically that in this one, in DECPAC by Clive Ruggles, you are going to have only one data, and you will get your direction. In declination on render, you can also use just one data, or you can include a file with several data on it, and you will get the declinations for each of your entries in this file. But I will concentrate on Clive Ruggles' tool DECPAC. Here we have it. This is the basic declination calculator. You can see that you include the latitude. You can choose between north and south latitude, of course. The azimuth in degrees, minutes and seconds, and the altitude. And here, when you press send, you will get a result. The results are going to give you the apparent declination here at the bottom, where you have there is minus 23 degrees, 41 minutes, 5 seconds, are the geocentric lunar declination. You know that if you want to compare with the moon, you need to take into account the lunar parallax, and then there is a shift, small shift, that you need to take into account in this case. You need to verify the program with the instructions that you have on the website that you can see on the top. Another tools that you can use, they are ephemeris software. For instance, there are plenty of them, either for Windows, for Linux-based systems, also for Mac OS. There are different software. Particularly interesting for archaeoastronomy, it might be this one, that is the visibility of planetary and stellar data by this Alcyone software company. This is the only free software that they have in this website, but it's very useful because you can calculate the first and last visibilities, the cosmical and acronical rising and setting for stars for several years in the past. For other platforms, also you can use different software. For example, for Linux, for Windows, for Mac OS, there is Stellarium. There is another lecture on devoted exclusively on stellarium on this course, so I will just mention a couple of things on stellarium later on, but let me mention here that you can also use stellarium to convert your data, your azimuth, your altitude and your latitude into declination. You can also use other software that you can see there. When using all these tools, you need to remember several things. First, the range of dates when these tools are supposed to be accurate enough. Many of these planetarium or ephemeris software, they are provided with range of dates when they are accurate enough. But when you try to extrapolate far in the past, you need to be very careful, read the manuals and see if your calculations, your renderings in this ephemeris software is going to be accurate for that time or not. This is very important. And also you need to take into account the calendar dates. Remember, we are using a Gregorian calendar, most of us, but for example, if we were in the Middle Ages, we need to take into account the Julian calendar in Europe, for example, or if you are in a Muslim or Arab country, we need to be using the Muslim calendar or many other calendars that they might be of interest at different moments. Remember, this introduces an uncertainty. If you need to do some of these calculations, always take this very much into account. Other tools that we can use is, instead of using local software, we can use online ephemerides, like the ones from NASA sites. An interesting site, for example, is this one, Horizons, where you can have many different ephemerides, and also this Eclipse website, where you have eclipses for many times in the past and in the future. Remember that these are sites for astrophysicists, and astrophysicists, they use the year 0, especially for obtaining ephemerides for eclipses. So when they use this minus 584, they mean 585 BC, okay, because they take into account this year 0, that it doesn't exist in the common era, but it is used in the astronomical calculations. As I said, stellarium is also very useful. Probably Georg Sotti is going to introduce many different aspects of stellarium. Let me just mention a couple of them here. The first one is the capability of introducing realistic profiles of landscapes, where once they are well calibrated and obtained, you can also use them to obtain further data to the one that you may have obtained in the field. For example, in this place where we are obtaining data from a newly discovered at that time platform in Petra in Jordan, we've measured the orientation to a given direction, that it was the main direction of the platform, but we could also later on extract more data thanks to these panorama pictures from introduced in stellarium. Also, we can use 3D rendering of buildings, of sites, or even digital terrain models that can be included in some of this software. For example, with SketchUp and Blender, we can do this 3D modeling of the sites. For example, the one that you can see here in this movie, it is from a megalithic monument in Galicia, in the north of Spain. that we introduced with the digital terrain model and the model of the 3D model of the site within Stellarium, and we could simulate the illumination phenomena inside the chamber at the time of winter solstice more than 5,000 years ago. And to finish this part of the lecture, let me just say that we have been using up to this moment single measurements. For example, we may be interested in unique cases like Stonehenge or Newgrange, and we might be interested in the probability that this orientation that they have is important, is compared to the probability that it is not out of chance alignment. To do this, we need to be very careful and perform some very specific calculations on the probability. And we need to be fair to the data. And this is what I was meaning at the beginning with this window from my house, where I could see St. James Cathedral and all this. There are many different directions in this window that I would have considered relevant on a first moment. So I would have to calculate that in each of these directions, what is the probability to have at least some of them that they are relevant or not. And once we do this, and if the probability of chance alignment is very small, is almost negligible, then I can say, okay, this single measurement is probably I can discard the chance alignment. But in any case, to be sure, I would need more data in any way. Archaeological, anthropological, ethnographical, wherever. Probably try to find similar cases. But in each of them, I will always have to be very specific, trying to find the context. The context is crucial and is going to be very important. It's not going to be part of this lecture anyway, but it is going to be the one that is going to give us the key information to understand if that astronomical event that might be related to the direction I'm interested is going to be relevant or not to the people who built and used that building. As I said a few slides ago, when taking a measurement, we will always try to do more than one trial. If I only take one trial, I'm not going to be sure if I'm doing the things correctly. Why? Well, we have here the target analogy, because if I only do one trial, I'm not sure if my measurements are precise or imprecise, accurate or inaccurate. So I would take a single measurement as an important one, and it is important to estimate my accuracy and my precision for the data. Let us see this with an example. Imagine that I'm trying to measure the orientation of this building. It's a church, for example. The important direction is the right the red arrow, but I'm not able, for whatever reasons, to take measurements in this direction. But I will take measurements from points A, B, C, and D. So I will need to manipulate my data to obtain the direction of the red arrow, but I will take the measurements from these other 4 points. For example, from point A, measuring a little bit from one point, then moving 1 meter in the back, 1 meter in the back or in the front, I will take a number of measurements. Imagine that I'm using a compass, and I take these measurements: 9.5, 10, 10.5, 10.75, etc. I take several measurements. From B, I only take 2 measurements for whatever reasons. From C, I'm going to take these other ones, and from D, just single measurements. It's difficult to measure from this corner, and I decide that with 1 measurement is more than enough. So then I have 14 measurements in total, and I can estimate a mean. For example, in the direction of A, I would just, for the measurements from C and D, subtract 180, sum the 14 measurements, divide by 40, and then I get this 10.4 with a deviation. This is the standard deviation of 0.4 degrees. Okay. Now, in the direction of the red arrow, I'm going to take the altitude of the horizon. I take this with a clinometer, and I obtain this altitude of the horizon of 4 degrees. So I have the mean of the measurements of azimuth is 10.4 with an altitude of 4 degrees, and I estimate, either with the magnetic models or by obtaining a reading of the sunset at that day, that the magnetic declination is 3 degrees west. This means that is minus 3 degrees. Then the corrected azimuth, remember that I'm using a compass, I need to correct this from magnetic declination, then the corrected azimuth is this 7.4 degrees. But this is the direction of A. This is not the direction of the red arrow. The red arrow, which is the axis of this church from the inside out, it is in the direction, I need to add this 270 degrees, so it is going to be this 277.4 degrees. Finally, with the formula for the declination, we can obtain where we have the altitude, we have the latitude, that I have it from a GPS, and the azimuth, this 277 degrees. I have a value for the declination. A value of the declination that in this case is 7.4 degrees. I can go to any of the ephemeris programs before to see if I can connect this with the setting, in this case, of the sun at any moment in the year at that position. And this is, for example, 9th of April, 3rd of September. It might be important, it might not be important, it depends a lot on the context, on the cultural context in this case. For example, if this is a church devoted to the Virgin Mary, it might be important if the 3rd of September is a festivity close to any Marian advocation or whatever. Or for example, there is a pilgrimage time to this church on the 9th of April. Then we could say, okay, then this church was built to have this into account. But remember that this has errors that we have measured before, that there is a deviation of a standard deviation of 0.4 degrees from my variations in the measurements. Also, the compass has an intrinsic error of 0.25 degrees. The remains, they may introduce some errors in here, like for example half a degree extra because the walls are bended, or they have collapsed and I don't see the direction very well. So also the altitude of the horizon is uncertainty, and then this can be translated into an uncertainty in my declination that is almost 1 degree in this case. And also this is going to be to translate into an uncertainty in the dates. Remember this. This uncertainty in the declination is going to be also translated in the previous case where I connected this with the sunset. This will translate in an uncertainty in the dates when the sunset is going to be observed. And this is for just one measurement. We can do this for a lot of measurements, and then we will perform statistical studies. As we said before, statistics are very useful because a single measurement could be very important, but if we don't have any other contextual information, we can try to contextualize that measurement, trying to find if there are similar items in the region and try to see if they have coherent orientations. Like for example, if I have a church, I can try to see if there are churches of the same period in the same area and if their orientation is similar among all of them or not. So this allows to verify if an orientation is anomalous or exists a pattern. Beware that there is no noise, in the sense that each building has been built with that orientation for a given reason. Another completely different thing is that we don't understand why that was the case. And in the absence of other data, this allows to verify the significance, not the meaning, but the significance of that direction. And also allows for introduction of modeling of different astronomical phenomena. For the data reduction, then this would be the next section. I will try to very briefly and fast explain a number of tools that we can use to extract and to analyze this data in the last 10 minutes of this lecture. The first tool that probably is used by most of us is Excel, where you can introduce in one of these books, and if any of you wants this, I can send it to you with the data reduction from azimuth, altitude and latitude into declination, where you can also try to map or to graph where are you going to have these concentrations of measurements. For example, in this case, you have different directions, and you can see that there are some peaks, some concentrations that they might tell us the directions that they are important or that they are more significant with respect to something, as we will see in a moment. Another tool that has been developed by Fabio Silva in R, it's a different software, it's Skyscape R. You can download it here from GitHub. It has a manual where you can set it up in your RStudio folder, and you can use it to produce a number of plots and statistical tests and so on, to see if your concentrations, if your directions, your preferred directions are important or not. In our group, we have been using IDL, which is Image Data Language, which is a commercial software. There is an open source version, which is a GDL anyone interested on these programs, I can send them to you and you can use them freeware. There are also some developments in Python that they can be used also on request. So how do we present and how do we show this data, our data, to the rest of the community? The first thing to do is to present the data, the final data, the data after we have corrected everything in a data table. In here, for example, we have the site, the structure that we have measured. These are different Roman sites where we have measured different things, like a sanctuary, like a temple, like different structures. Here we have the latitude, we have the azimuth, we have the altitude. These are the measurements that we have to obtain. We have the final declination that we can connect to the astronomical bodies, and here, as further information, we give, for example, the relevant dates connected to these directions, or the relevant astronomical items that we might be interested in. One of the first graphical tools that we tend to use are the orientation diagrams, or also called Hoskin diagrams, because he was the first to use them in a very wide manner to show the orientations, the directions of monuments. In this case, for example, it could be the monuments in the direction of the temples in the southern part of Jordan. And you can see that, for example, these are going to give only the azimuth. We are not giving the information on altitude, and this is a problem, but it may provide a first handle on seeing if the data is spread everywhere or there are certain directions that seem to be important. The data is normally given within the circle. The circle is providing the azimuth, the horizon, while the outside marks provide the cardinal points and interesting rising and setting of the sun or the moon or whatever. Another tool are histograms and curvograms. Normally, in many studies, we see the use of histograms. The problem with histograms is that they need to be very well treated so that the data is not poorly treated in this way. For example, in the top right, you could see that we could beam the data towards south, winter solstice, equinox, summer solstice, north, and I could see how there might be some larger concentrations towards summer solstice or the south. But between south and winter solstice, there is a wide range of directions. And I'm somehow here blurring too much my results. A way to try to be more, to extract a little bit more of information from this data could be the curvograms. This is the one that you have on the left, where you for each of the data, what you're going to have is a small distribution of probability distribution. So to say, imagine that my direction of interest is this one, but I see that my important direction might have some uncertainty in this area, like say few degrees or a few tenths of a degree or whatever. When I combine this data with a lot of data from different sites, I might end up with a distribution of probability, a distribution of directions. This is what I have here in the left. In the left is a histogram, but each of the data is modeled by a small Gaussian, and when I sum each Gaussian on top of each other, I can see that there are some concentrations at different directions. So these provide probability density distributions that they can be used as curvograms, and they may give us a significance. For example, is this peak here more significant than the peaks at other directions? The peak at zero declination is more significant than the peaks at declination 24 or minus 24. This is something that we need to ascertain with respect to something. For example, if I used a homogeneous distribution along any point in the horizon and convert it into declination, I will see that I have something like the blue line in this plot of the declination. If I choose random points, I will have something like the black line in this plot. If I compare it with the positions of the sun each day of the year, what I would expect is a distribution like this one with two maxima on both solstices and a minimum on the equinox. Compared to the moon, it is very similar to the one of the sun, but mind that the range of declination is going to be a little bit wider, and the maxima are going to be located in a different position. So with this, I could make different tests and try to see if my declination, my plots are significant or not. I won't go into details here, but I could also try to use this on top of maps where I can show the directions of the monuments of interest within the map, try to see if there are regional areas with specific orientations, also heat maps that they can be used for this. Also the curvograms could be used for, they can be used for modeling and try to disentangle if different bodies are the targets for given direction and so on. This allows to take into account the behavior of the sun and the moon at different epochs within the year, and comparing also different groups of different monuments and orientations. So at the end, we could use different modeling and statistical techniques, Bayesian inference, Kolmogorov, Cowper tests, cluster and factor analysis, multivariate analysis, very many different tests that can be used. To end, let me say just that in any case, software is a tool. Try to be always fair to the data, and please keep the cultural context in mind. This is very important, the context. Thank you very much. I'm sorry not to be there, but I hope that if some of you will be there next week and you still have doubts and questions, probably more than what I would like, I will be ready and willing to answer any of them. Thank you very much. See you next week.
We're gonna come back in 25 minutes and we'll see you all shortly.
Achievement, given the guys got COVID. My
I know,
goodness.
right?